last week we started to learn this economy with uncertainty, and we introduced this important concept of state contingent goods. State 1 good, state 2 good, state 3 good, or state 1 potato, state 3 potato, and the prices of state contingent goods are called state prices, in short, state prices or allowable prices. So let's solve one basic question on state prices. So suppose there are 4 possible states in the future: state 1, state 2, state 3, and state 4. And from today's point of view, we don't know which state will realize. There's an asset X, a share of some company, and we perfectly know the payoff of this asset in each state. We just don't know which state will realize. If state 1 realized, then the payoff will be 150 pounds or 150 pounds of potatoes. If state 4 realizes, then the payoff will be 90 units of potatoes or 90 pounds. Okay? And there are call options associated with this asset. So this is the payoff of asset X, and on top of that, we have 3 more assets, call options for this asset X with strike price 90 and call option with a strike price 110 and call option with a strike price 130. And we know the value of European call option at the maturity date. That is the value, the price of the underlying asset minus the strike price, or 0, whichever is larger. So if state 1 realizes, the value of this call option with the strike price 90 is 60. In state 2 it's 30. In state 3 it's 10. And in state 4 it's 0. For this call option, the second call option, the value will be 40, 10, 0, or 0. And for the third call option, 20, 0, 0, and 0. Now, we don't know the state prices, the price of 1 unit of potato at state 1. Okay, we don't know these state prices, but the idea is that suppose we observe the market prices of these assets, X and these call options. Theoretically, any asset is regarded as a basket of future consumption goods, right? So if we don't observe P1, P2, P3, P4 directly, but the idea is that we can guess these state prices from prices of other assets. Theoretically, the price of this asset X should be 150 times P1 plus 120 times P2 plus 100 times P3 plus 90 times P4. Because this asset is a basket of 150, 120, 190 units of future potatoes. The current price is 99. This call option, the theoretical price should be 60 P1 plus 30 P2 plus 10 P3. The current price is 18. Yeah? So, basically we end up with this, answer is posted. Just this is a reminder to refresh your memory. We end up with this system of 4 linear equations implied by the current market prices of these 4 assets, and we can guess the state prices. And make sure, okay, you are 30 years already, so as soon as you see this type of system of linear equations, you can immediately rewrite it in the matrix form, yeah? That is to say, you can have 150, 120, 100, and 90 times P1, P2, P3, P4 equal 99. Yeah? And 60, 30, 10, 0 times P1, P2, P3, P4 equal 18. And so on. So P1, P2, P3, P4 is simply equal to the inverse of this payoff matrix times the current prices of these assets. This is how you guess state prices from the observed market prices of other assets. And once you have state prices, you can price any asset. What is the price? For example, what is the price of a risk-free bond? That will give you 1 unit of potato, whatever state realizes. That's the basket of one of each potato. So the theoretical price today should be P1 plus P2 plus P3 plus P4. If you have these, just sum them up, and the current price of such a bond is 0.9. Okay? Yeah? Is it fine? So the risk-free rate is inverse of that. I mean, gross interest rate. Okay, so as long as we know all the state prices, we can price any asset. State contingent goods are like essence or atoms or molecules of any asset. Any asset, theoretically any asset, is composed of many different state contingent goods, and as such the price of any asset is the total value of the basket of many state contingent goods. So if we know P1, P2, P3, P4, the current prices of future state contingent goods, as long as we know the current prices of future state contingent goods, we can price any asset. So the next question is how these state prices are determined, P1, P2, P3, P4. These state prices are determined in economic equilibrium with utility maximizing consumers and market clearing conditions, demand equals supply. But the story is not very different from normal economy with normal goods, apples, bananas, coconuts. If you'll see, think about an economy with apples and bananas and coconuts, then the utility function of consumer looks like some coefficient U1 times eta A1 times U of consumption of apple, apple consumption, times U plus U2 A2 times U of banana consumption plus A3 times U of coconut consumption. And you are familiar with this. An example is a famous Cobb-Douglas function, such as C1 to the power A1 times C2 to the power A2 times C3 to the power A3. Okay? If you take log, you have this additively separable utility function. Yeah? And then we studied in week 8 and 9, we studied this environment, dynamic environment. There is only one kind of consumption good, generic consumption good. No bananas or apples. There's only one kind of generic consumption good, but there are many dates, date 1, date 2, date 3. So dynamic environment with many dates, date 1, date 2, date 3. Then the utility function typically is assumed to be well, U of today's consumption amount plus some discount factor beta times U of date 1 consumption plus beta squared U of date 2 consumption and so on. Again, additively separable utility function. What if we have uncertainty so in the future there are many possible states. Economy can be good, can be bad. There are states 1, 2, 3. Well, and then the utility function looks like this. Q1 UC1 plus Q2 UC2 plus Q3 UC3, where C1 is the state 1 consumption, C2 is the state 2 consumption, C3 is the state 3 consumption. Okay? You value all of them because it would be horrible if you have to starve in state 1, even if you have plenty of consumption goods in state 2 and state 3, it would be horrible if you have to starve in state 1. So you value not only state 2 good and state 3 good, but also state 1 good. Now, most of the time, it is assumed that these coefficients are probabilities. So Q1 is the probability of state 1 realizing. Q2 is the probability that state 2 will realize in the future. These are the likelihood of these future states. So you can rewrite it. The shorthand notation of this utility function will be expectation of U of future consumption. Okay? And this type of utility function, when there is uncertainty in the future, is called von Neumann Morgenstern what utility? What utility? There's E here, so you know. Come on. Probabilities, expected utility, thank you. Okay? So you can see that the stories are different. Apples, bananas, coconuts economy, or dynamic environment, or economy with uncertainty. Stories are different, but you can see that mathematically, they are not very different. Okay? So let's see that. Let's look at one question on the general equilibrium with uncertainty. And you'll see that the math is very, very similar to what we have already seen. And here's the setting. There are 3 possible states in the future. State 1, state 2, state 3. So let's denote the consumption in state 1, state 3, and in state 1, in state 2, in state 3 as C1, C2, C3 respectively. And there are homogeneous many consumers. All of them have this expected utility, the same homothetic preference, and the probabilities are 0.5, 0.3, and 0.2. Okay? U function is given by this, our familiar CRRA utility function, power utility function, with relative risk aversion parameter gamma equal 0.5. The endowment is 181 and 64. So today, we don't know which state will realize, But we perfectly know that if state 1 realizes, the consumer doesn't know which state will realize. It may be state 1 or state 3, but he perfectly knows that if state 1 realizes, he will have 100 potatoes. He knows that if state 3 realizes, he will have 64 potatoes. He just doesn't know which state will realize. Question. What are the equilibrium prices of state 2 good and state 3 good? Let's make the state 1 good as numerator. So let's normalize the price of state 1 good to be 1. What are the equilibrium prices of state 2 good and state 3 good? That's the question. And what's the general equilibrium? General equilibrium is the combination of the utility maximization and market clearing, demand equal supply. So first, consumers maximize their utility taking prices as given. So they are price takers. And the prices must be such that the total demand is equal to total supply. This is the pure endowment economy without any production. So the total supply is simply equal to the total endowment of the economy. So the utility maximization problems look like this. Objective function is the utility maximization. We are going to maximize this with respect to C1, C2, C3. This is the budget constraint, the total expenditure. So let's denote by P1, P2, P3 the current prices of these future state contingent goods. The current prices of these future state contingent goods. So today they trade future goods following these prices, okay, without knowing which state will actually realize. And the total expenditure should be equal to the total wealth. And for the consumer, the total wealth is simply the total value of his endowment. Everyone has the homothetic preference, so we can justify the existence, the use of the representative agent. So we can act as if there is a single consumer whose endowment is equal to the total endowment of the economy. Yeah? Lagrangian function looks like this. Objective function plus Lagrange multiplier times the budget constraint. And we differentiate this with respect to C1, with respect to C2, with respect to C3, ending up with 3 first-order conditions. If we differentiate this with respect to C1, we have Q1 times U prime C1 plus lambda times negative P1. And that should be equal to 0. That's the first-order condition. And so on. So we have this, we end up with these 3 equations. U prime C is equal to C to the power minus gamma, where gamma is 0.5. So this is equal to 1 over square root C. Okay? This part is equal to square root C. And this is the representative agent economy. We know that prices, equilibrium prices, must be such that his optimal demand is equal to his endowment. Okay? So in equilibrium, C1, C2, C3 should be equal to Y1, Y2, Y3. So representative agent assumption implies this for I equal 1, 2, 3. So we substitute this market clearing condition into the first order conditions, ending up with these 3 equations. Yeah, you can substitute this market clearing condition from the representative agent assumption only after you get first order conditions, okay? You cannot substitute at the very beginning yeah, consumers don't think like, okay, this is a representative agent environment, so I should demand what the economy has. Yeah, they don't think that way. They are price takers. They just maximize. They do what they do their best. So yeah, make sure you substitute these market clearing conditions only after you get first order conditions. And then yeah, our assumption is that yeah, let's normalize P1 to be 1. Probabilities are 0.5, 0.3, 0.2. The endowment is y1 is 100, y2 is 81, and y3 is 64. So the first equation gives you lambda, right? 0.5 over square root of 100, that's 0.05. And once you have lambda, then the second equation gives you the equilibrium price for the state 2 good. That's 0.3 over square root of 81 divided by lambda, that's 2/3. And the third equation gives you the equilibrium price of the state 3 good, 0.5. So in this economy, if this is people's preference, and if these are the probabilities, and if these are the endowment, the equilibrium price of the state 2 good is 2/3, and the equilibrium price of the state 3 good is 1/2. The likelihood of state 2 and state 3 is relatively small, but they are not so cheap in equilibrium because they are scarce compared with state 1 good. Okay? Now story is very similar, even if you have dynamic stochastic environment. So there are date 1, date 0, date 1, date 2, date 3. There is present in future, and there is uncertainty. You don't know which state will realize in the future. Let's start with a simple case. So suppose, let's say there are only three dates, date 0, 1, 2. And let's simply assume that there are only two possibilities. At date 1, the economy can go up or go down. And then at date 2, again, there are two possibilities. The economy can go up or go down. And the economist idea is that even if they are the same consumption good, if time is different, they are regarded as different commodities. If states are different, then they are regarded as different commodities. Okay? Here we have 7 nodes. We have 7 nodes. Node is just a combination of time and state. So let's label them. Let's label consumption at each node as C1, C2, C3, C4, C5, C6, and C7. And consumer values all these consumptions because he wants to consume every day and he wants to consume in any scenario. Let's denote by Q the probability of each node being reached. So, yeah, Q2 is the probability that this particular node being reached. So these are probabilities. So yeah, Q1 is simply 1 because we start with this node. So the probability of this node being reached is simply 1. And Q2 plus Q3 is equal to 1 because at date 1, economy is either go up or go down. Economy is either up or down. So Q2 and Q3 are equal to 1. And Q4 plus Q5, the probability of this node being reached and the probability of this node being reached should be equal to the probability of this node being reached. So Q4 plus Q5 is equal to Q2, and the probability of this node being reached and that for this node is equal to Q3. Utility function of a consumer in this environment looks like this. So he maximizes his utility with respect to C1 through C7. And the utility function is, well, depends on C1 through C7. And it is from the date zero consumption plus some discount factor beta times the expected utility from the date 1 consumption. Okay, this is expected utility date 1 plus beta squared times expected utility from the date 2 consumption. Okay, this is the expected utility from the date 2 consumption. Beta is the time discount factor and Q's are probabilities. So you're summing up expected utility for each date. Again, this is just the additively separable utility function. So even if the consumer has this type of utility function, you can easily imagine that you can get general equilibrium price in the representative agent economy, as long as you know, well, the preference you already know. So you know, if you know the endowment, you can get the equilibrium prices of this good, and so on. So let's denote the prices by P's, P1, P2, P3, P4, P5, P6, and P7. So these are the prices. Yeah, let's say the current good is the numerator. So let's normalize P1 to be 1. So these prices, P2, P3, P4 up to P7, are the current prices of these future state contingent goods. So today, they trade future goods according to these prices. And our goal is to find the equilibrium prices, okay, the prices in the equilibrium. Lagrangian function is utility function plus Lagrange multiplier times budget constraint I forgot to write budget constraint, but you know budget constraint. The budget constraint is total expenditure is equal to total wealth. Total wealth is total value of all endowment. I forgot to tell the endowment, so let's say endowment is given by Y's. Y1 is the amount of consumption good the consumer has at date 0. Let's denote endowment by Y. Be sure which variable is exogenous to the model and which variable is endogenous. We know the probabilities Q's. Q's are given. We know the endowment. Endowment is given. Our purpose is usually endogenous variables are prices and demand. So usually these P's and C's are endogenous, but in the representative agent economy, equilibrium demand C's will be simply equal to Y's. So practically, only P's, prices are endogenous. Okay, we want to find equilibrium P's. Okay? This is the Lagrangian function. We differentiate this with respect to C1, with respect to C2, and so on. If we differentiate this with respect to C1, we have Q1 times U of C1 equal lambda times P1. If we differentiate this with respect to C2, we have beta times Q2 U prime C2 star equal lambda P2. With respect to C3, we have beta times Q3 U prime C3 equal lambda P3. With respect to C4, we have beta squared Q4 U prime C4 star equal lambda P4, and so on. We have 7 equations in the first order condition. And the representative consumer assumption, representative agent assumption, implies this. So we substitute C1 is Y1, C2 is Y2. So we can get lambda and prices. I mean, the utility function doesn't have to be like that, obviously. This is the simplest macroeconomic model, okay? If you pursue further study in economics, you will study more complicated, more realistic utility functions or endowment process, but the idea is the same. There's utility maximizing consumers, profit maximizing firms, and yeah, you end up with n equations for n variables, solve them, and that's the market equilibrium prices. Okay? So we have environment that's preference, and endowment. And the general equilibrium gives you all the state prices. And once you have all the state prices, you can price any other asset. Okay? Again, state prices, state contingent goods are atoms, essences, molecules for assets. Okay? So any asset is a basket of these state contingent goods, so the asset can be priced as the total value of the basket. Okay? Good? Good.